Chao Ji obtained her PhD in civil engineering from the University of Miami. Her PhD project was on the development of SOSim as a response to the Deepwater Horizon event funded by GOMRI, which is an acronym for the Gulf of Mexico Research Initiative. Chao currently works as a postdoctoral research fellow working on the computational toxicology for chemical risk assessment. Are you out there, Chao? Okay, it looks like you're, there we go. We can see your presentation is not in presenter mode yet.
Okay.
There we go. Perfect, we can see you, we can hear you.
Welcome everyone. Thanks for the organizer having me to this amazing workshop. Today I'm gonna introduce you SOSim, the submerged oil simulator, a Bayesian model for checking submerged oil. The content of my presentation today is what I did during my PhD study at U Miami. So let's get started. Back to 2010, a Deepwater Horizon oil spill happened in the Gulf of Mexico. A blowout caused the explosion and led to the Deepwater Horizon oil drilling platform to sink. Oil released for 3 months. In total, 5 million barrels of oil was spilled to the deep ocean, causing the largest marine oil spill event in the history. In this devastating oil spill, around 40% of oil was submerged in the water column. The oil was submerged at depths around 1,000 to 1,300 meters. That depth range is governed by water density. The oil was existed at a constant density layer. It's also named isopycnal layer. The figure here gives you a picture about the distribution of submerged oil in the water column. The red dashed line represents the potential depths of the isopycnal layer. The brown dots represent the oil droplets and the dash represent the dissolved oil. The kind of oil lasted in the water column for several months. Locating the distribution and checking the submerged oil in the deep ocean is very challenging because the invisible and deep features of submerged oil. Also because the lack of information on where to find the oil. And the submerged oil can only be detected by sensor deployed in the deep ocean or by collecting the water samples. The figure here shows you the collection of water samples during the Deepwater Horizon response period. This kind of operation takes around 2 to 3 hours, so only few data can be collected using this method. So without the information on where to find oil, the efficiency was very low. To deal with that kind of problem, SOSim is developed to help locate and check the movement of submerged oil. SOSim is a Bayesian model. So first, what is Bayesian? Imagine when you flip a coin, what is the probability to flip a head? Frequentists will say like 50%, but Bayesian method doesn't agree. See the penny here with a Lincoln on the head and a memorial on the back. The side with Lincoln's head is a bit heavier than the flip side. So the coin's center of mass lies slightly towards heads. The spinning coin tends to fall towards the heavier side, leading to the probability of having a head is 80% instead of 50%. That is the difference between Bayesian method and the frequentist. Bayesian takes not only the ground truth, but also the prior information into consideration, such as the weights of each side of coin. So in that case, the weight of coin is the prior info, and the experiment, the flip coin experiment, is the ground truth. Bayesian model use of the information to construct a posterior distribution, which leads to a 80% head rate instead of 50. In SOSim, we used the same concept. The limited field observation on oil concentration is used as ground truth, and the density layer of isopycnal layer and outputs of other models are used as prior info. The output of SOSim model is a posterior distribution of submerged oil. We use Bayesian method because it has its unique features. First, the Bayesian model can access probability based on limited information, which is suitable for the submerged oil in the water column. Although this kind of inferred probability can be updated when new information is available, so it can predict the distribution of submerged oil in real time. Here is an overview of SOSim workflow. The submerged oil concentration field observation are used as ground truth. If the trajectory model prediction of submerged oil distribution, such as Oscar outputs, are available, they can be used as prior info of the information input to SOSim. Here is a graphical user interface of SOSim of the information related to the oil spill is collected here. And after all the information is ready, and SOSim is ready to run. And SOSim will generate a probability map with different color, represents the relative concentration of finding submerged oil in 3 dimensions, indicating locations and depths of finding the oil. The confidence bound will also be provided. Here is an enlarged graphical user interface that is used to collect the user inputs, such as available field data here, the prior info, and the resolution, and in the prediction dates. After all of the information are collected, click the calculate. It will show the results on the GUI and indicating the location on the world map. Next, I'll show you 2 case studies of applying SOSim to model submerged oil distributions. First is a synthetical case, and second is using data from the Deepwater Horizon. The inertial circle case is generated for the model validation. The parameter generating this kind of synthetic data are summarized here in the table. And the current moves in the northeast direction on the first day, and the southeast direction on May 2nd, southwest on May 8th, and finally in the southeast direction. These data are plotted as red dots in the figure here. On each day, there are like 29 field data. And SOSim assimilates this data and predicts the submerged oil distribution on the same day as field observation. The prediction are plotted here in the in color maps. So the model's prediction agrees well with the data moving tendency and almost covers the field data and the moving direction on the same day. The SOSim inferred parameters are also summarized here. Comparing values in the 2 tables, the moving direction are correctly inferred and the errors are very small. So this study demonstrates the ability of SOSim to infer and predict trajectories that have a time varying velocity vector. Next case study is a Deepwater Horizon oil spill. SOSim is applied to predict the submerged oil trajectory. Here is a cumulative trajectory prediction from Oscar. It shows a southwest and northeast direction. A systematic random sampling method is used to sample across the area of interest. These sample data are plotted as gray and red dots here. The gray dots represent location without oil. The red dots represent location with oil predicted by Oscar. of the available field data in the same time period as OSCA model are used. The field data are blue dots here, showing a southwest direction. In SOSim model, a novel prior likelihood is developed to balance the effective number of prior and field data. All of the data plotted here are input to SOSim for predictions. It's loading. Okay, here are the SOSim prediction on May 26, which is one day after the data. Figure here overlaid with the model inputs. The field contours represent the relative probability of submerged oil. The green line represents the 95% confidence bound. The dashed contour line shows the depth of the isopycnal layer containing submerged oil. Blue lines represent the lower depths of the isopycnal layer. Yellow lines represent the upper depths of the isopycnal. As indicated in the figure, the submerged oil in that area are concentrated at the depths of around 1,000 to 1,300 meters. The submerged oil patch appears to be distributed in the west and southwest directions. This prediction agrees with the field observation, which was reported that oil was distributed in the southwestern direction. Although no observations were made in the northeastern side, the prediction with prior also shows a weaker northeastern distribution, accounting for OSCA data, but with a lower probability than the southwestern distribution. SOSim prediction on June 4th, 10 days after the available data is shown here. Results here suggest that oil patch moves and is dispersed further to the south and southwest. Here is detected submerged oil made by a scientific team in almost the same time period as the prediction here. It also shows a southwest distribution. So the predicted moving tendency in the left figure here agrees well with the detected distribution in the right figure. So obviously, SOSim's prediction is reasonable. So with predictions, SOSim can be applied for the water column data collections during the emergency response. First, initial field data are collected using the environmental sampling procedure, such as systematic random or adaptive systematical sampling method, etc. Sampling devices like ship-based rosette and AUV can be used. Sampling plan may vary among different devices. So after the collection of initial data, those data can then input to SOSim, and SOSim to make future forecasts with a probability map output. An area with high probability of oil presence is determined, and new field data can be collected within SOSim predicted area of oil presence. So this whole process can be repeated to collect new field data. And with the new field data, SOSim can update its prediction in real time. So another case study we did here is to test the efficiency of using SOSim to guide the sampling procedures. In this case study, because of the lack of field data on submerged oil, OSCA simulation on submerged oil following the Deepwater Horizon spill is regarded as a real distribution. Using sampling plans in SOSim, assimilates sample data and generates a prediction. And then SOSim prediction is compared with Oscar simulation on the same day. Here is sampling results using naive zigzag paths and is designed based on the empirical considerations of the moving directions of submerged oil. Devices like AUV could travel from the among the paths to collect water samples. Those red dots are the sample data. And the sample data input to SOSim for a prediction. Here is SOSim's prediction results overlaid with a real distribution. SOSim's prediction shows a similar moving tendency as a real distribution and achieves like 90% correct prediction rate. With initial data, SOSim then makes prediction one day after the data were collected. The same method, naive zigzag path, is designed within the uncertainty regions predicted by SOSim to collect water samples. The new sample data is also like plotted as the red dots here. The new data input to SOSim, and SOSim make a time updated prediction in the right figure here. Similarly, the prediction overlaid with the real distribution compared with previous results here. With the new information, SOSim gives a narrower and more certain prediction. This prediction achieves like 85% correct prediction rate. So let's wrap it up. SOSim is a data-based Bayesian model. The novel aspects of SOSim include first, the use of field data as ground truth, and second, the prediction from other models and the density range of isopycnals are used as priors. SOSim is also a probability model, so SOSim can easily give the uncertainty estimates that meet the ASTM standards. Overall, through all the case studies I went over, SOSim is able to predict the submerged oil distribution after a subsurface oil spill. SOSim can also follow the inertial currents that change direction in several different time steps. Overall, SOSim has a great potential to be applied to guide the sampling plan of water sample collections during the oil response period. This is one future research direction that we hope SOSim can be applied for. The SOSim model can be applied for a mysterious spill where the oil spill location are not known to. So SOSim can make the location as unknown parameter and estimates the location. There are like two case for the mystery spill. One is like 2 years ago. There was a mystery spill in Brazil that threatened marine biodiversity. And also yesterday, a mysterious spill covers Israel's coastline in toxic tailboats. Israel bans sales of all seafood after the spill. So to deal with that, SOSim can like using the probability method to make estimates of the spill locations and like infer the locations. So that is an open question to discuss. Great work comes from great team. This research is supported by Gomery and my advisor, Dr. James Engelhardt and Dr. CJ Beagle-Cross, and my partner, Mary Giacchetti, also contribute to this project. I want to say thank you to them. Also, thanks for your time and thanks for your listening.
Thank you, Chao. It's really interesting to see. I mean, as we know from surface spills, we rely on typically NOAA for trajectory data. and it drives efficiency. How quickly can we figure out what's where and where it's headed and where it's going? And that is something that is, we talked about just before your presentation. It's something we're challenged with in terms of submerged oil. So that's really useful, and certainly looking backwards the other direction, as you say, I know Jordan Stout, who was before you, talks about a time when they were trying to figure out how far they needed to drag a whale carcass off the beach so that it wouldn't wash back up during the 4th of July holiday in Los Angeles. There's so many uses for modeling and trajectory understanding. Jenna, do we have a question here?
Yeah, we have a couple questions actually.
Okay.
First one is going to be from Lee Britton. The Bayesian method is kind of an automatic inference engine, and this raises concern with people who have applied experience who may believe different methods work well in different settings. Do you feel like you maximized field observations to their best abilities?
Yes, that is the advantage of like using Bayesian method. Since for other kind of trajectory model, they are basically based on the historical observations like the velocity and diffusion coefficient. But like in in reality, the situation might be different. So the advantage of SOSim is like taking use of that kind of field data and simulate those data to infer the velocity field instead of using the historical data. Also, the historical data is used as a prior info as in SOSim model. So it combines the prior info and the field observation. So that is an advantage, I think.
Great. We have another question. How does SOSim differ from OSCAR?
That's a great question. OSCAR is a trajectory model. So like it requires the velocity field and also the detailed information of the oil droplets and or other kind of oil chemistry related information. So they start from like the time zero and forecast to the future. But like for SOSim, we can start like if there are field data collected on the like let's say 7 days after the spill. So SOSim can assimilate that data and predict into the future and also check back to the initial stage of the spill. So that's why we think SOSim will be useful for the mystery spill that like with unknown spill location. So after we have those data, we can check back to the initial release location and tell the Coast Guard or the oil responders where the possible location is. Hope that answers your question.
I think so. Thank you so much. I think that's all of the questions I have.
Yeah, thank you so much, Chao, for sharing that with us. That's terrific work. And that brings us to the end of today's session.